The concept of refraction is similar in nature to reflection. Reflection involves a redirection of a wave. A redirection, it bounces off. Refraction, instead of redirecting, is just altering. It's altering, it's changing the way the wave is traveling. It's bending it a little bit. It's causing it to slow down or speed up. Imagine, I'm going to give you a perfect analogy for this that you will not, you don't have to think of anything else. The easiest way to remember this. Imagine that you're walking and then suddenly, as you're on the beach, you suddenly walk into a level of water. Are you able to walk as fast as you were walking a moment ago? Obviously, right? No. What happens? What happens? Physically.
Well, you're getting slowed down by the water.
Yeah, you're getting slowed down by the water. Anybody know the word for that? Very good. That's the exact explanation. What's the word for that when something like a fluid slows you down? Because right now, believe it or not, the air is slowing you down. The air is actually slowing you down. You're in a fluid. Gases and liquids are fluids. When you're in a fluid, it involves some sort of a force against you. And you can feel it if you do this, right? Do this. You feel wind on your arms. You do this under the water, though. What do you feel? There's something else there. What is it? Okay, water resistance. Good. That's another way of putting it. Anybody know what the name of the force is? I've used this word, I think, once in class before. Once. I talked about those pistons at the top of the door, which cause the door to go like and slow down as they're closing. I use the word, so it's the letter V. Anybody remember this word? Yeah. Yeah, viscous force. I used that word just once. You didn't have to write it down or anything. The idea of moving through a fluid is feeling a resistive force that's proportional to the speed at which you move. The square of the speed, really. So if I take my arm and move it under the water or through the air very slowly, and then I move it faster, you can feel the air. Because you're moving your hand faster, the air is pushing back with more force. The viscous force is a fluid resistive force. Now, I'm in a fluid right now that's pretty, I would say, I use the word light. It's not dense. Air is not dense. Water molecules are much more dense, right? It's an actual liquid versus a gas. They're both fluids, though. So as I actually walk through water, not on water, but walk through water, I feel a viscous force which slows me down. That's what's happening with refraction. When an EM wave travels through a new medium, that medium, its density, its thickness, is what's slowing the wave down. Again, light travels through the air. It travels through a vacuum in space at the speed of light. As soon as it hits our atmosphere, we see blue because it slows down. And we're seeing what's called refraction. It's blue light, the bending of light. Now, when it enters that pane of glass right there, that pane of glass is, in a sense, thicker. It has a higher, we'll say, what's going to be called N value. It's thicker than the air around it. So the wave is going to then slow down even more. Okay? It's going to bend. It's going to change direction. That's the whole concept of what we're getting at. A lot of this from this point on is going to be math. You're going to see math. You have to understand what's happening. The wave itself is traveling. It hits another boundary of a surface, and it bends. Okay, it actually changes the angle at which it's coming in. Ernest, go ahead and ask before I go to the diagram.
Forget it.
You sure?
Yeah. I was just going to ask, so is it basically the medium?
The medium, yes, that's the word. Good. That's right. The medium itself is what we're looking at. So, when we see this, we're going to see for an example to start, when we have an EM wave traveling through air, and then it hits a window. Okay, here's the window. So it's coming in from the sun. It hits the window. It would want to continue on the path it's traveling at. That's the path it would want to continue. Some of it gets reflected, right? Think about light hitting glass. Some of it gets reflected back out. Obviously, we know when light even hits a surface like a white surface, we know the light is actually all getting reflected. None of it's passing through. We talked about that in the last section with colors. Now, with a transparent medium like glass, part of it gets transmitted through, part of it gets reflected. The part that gets transmitted through, theoretically, should follow the same direction. And if I continued this line, I would follow along this blue line here. But instead, what happens is the wave fronts slow down. They slow down. And as a result, they bend toward the normal. Okay, again, let me explain. So the wave should follow this direction here, but instead, when it hits this boundary, the new medium slows it down like molasses. like your arm getting slowed down by water. And as a result, this actually bends. The airplane went out. Damn. So, again, to reiterate so you guys can see, it would want to travel in this direction. But because this new medium interface, when it hits right here, slows it down, it bends this way. Which means it bends, follow the direction here, toward the normal. This is the normal here. So this wave, instead of being here, is bent toward the normal. Maybe jot that down. That's something you're really going to want to know. Okay, it's going from air to glass there. It's slowing down. So you could jot down that it slows down here and it's bending toward the normal. And just use common sense. Think about your actual motion. If you just suddenly were running through water, you would be slowing yourself down. Water, glass, they're both thicker materials than air. Now, what's going to happen in the other direction, obviously? Conclude, please, on the right side.
It goes away from
Yeah, very good. So we go from a medium like glass, and then we go into air. When would you see that? That's a flashlight. Think about a flashlight. The light comes out of the bulb. Isn't there a lens on the front of the flashlight? There's actually a lens behind it, a transparent glass, whatever. But it goes through glass, gets bent, and comes out into air. When something exits a slower moving medium into something like air is the fastest moving medium possible, a vacuum, we assume, but air itself, it's going to speed up, and when it speeds up, instead of going in this direction, which it should, right, it should continue in the direction it was coming through. That would be the direction, really. Instead of going in that direction now, because it speeds up, it bends away from the normal. Here's the normal right here. And instead of the wave continuing on its path, it bends away from the normal. So speeds up, bends away from the normal, slows down, bends toward the normal. Now, the reason I go through this theta I part for the last section was because now theta I is still that same angle. But please write this or underline this in big letters. Theta R is not the angle of reflection. Reflection, it's just the same angle as theta I. You don't have to do anything. There's no need to even denote it. Okay, remember, for reflection, the angle that it bounces back at right here is the same as this. These are identical, these two angles here. Okay, these two angles I'm pointing at are identical. But these angles are going to be different because it's bending itself. Okay, it's bending itself. Hey, to show you some quick images, and this is what I was talking about, look at the image on the left. Okay, all that is the bending of light. It looks like the person's finger is literally chopped because literally in this area, light gets bent based on the medium, the material. It's like a thick slab of glass. It's a lens from the side. So it's bending the light so it looks that way. If you've ever looked down the road before and you see it looks like oil or it looks slick, it's actually not oil. If you see like a rainbow looking thing, it might be oil. Because oil does actually disperse light into the colors of the spectrum. But when there's not, what you'll see is actually that the heat from the road is kind of emanating upward. That's a fluid. The gas rising is actually a fluid. It bends the light to make the surface look slick. But that's actually refraction also. That could be reflection, though, if you see the light getting bent back and all the light's getting dispersed in color. If there were actually some oil or some sort of a fluid on the surface, that would disperse light. All right. Now let's go right into what gives us these values then. So for materials, we have properties. For example, this piece of wood is more or less dense than this book. Well, clearly it's less dense. You could hold this piece of wood very lightly. It's less volume also, but the density of this is a lot less. The fibers are separate, right? All the molecules are further apart, where the paper is pretty compact, even though it's the same material, right? You got the book from wood. You're going to pick up on that, right? It's really the same material. But this is more dense than this is. Well, the same thing occurs here. We have ratings for different media. The ratings are called indices of refraction. And the index of refraction is actually the thing that tells you if it's going to slow down or speed up. If it's going to bend away from the normal or toward the normal. Air has the lowest index of refraction. And the rating for these values, just to give you an idea, comes from the ratio of the speed of light, c, which is what again? Anybody remember that number? What is the value of c? Yep. 3 times 10 to the 8 over Now v is the actual speed of light in that medium or material. So for example, let's see if I can make one work nicely. Yeah, for glass, the value here would actually be 2 times 10 to the 8. That's the speed of light in glass. I just want to use this as an example to show you. So if you wanted the n value, the index of refraction for glass, you just take a look at that ratio. What happens to 10 to the 8? What happens to 10 to the 8? What's 3 over 2? As a decimal ratio. What as a decimal usually represented? Yeah, 1.5. That's the value of the index of refraction for glass. Now, can we do a lab with this in class? Can you measure these speeds?
No.
You're not going to measure it anytime soon, no offense. Not you, but me too, right? You need tools way beyond what we have in the lab to be able to measure the speed of light as it travels through glass. Now, if theoretically we could find a way to have the piece of glass big enough and slow it down enough, maybe we could actually give an estimate, but these values are values I'm just pulling out of a table right now. Okay, they're experimentally determined, but they're determined like the values of mu. They're inherent properties of the materials.
The unit for this?
What do you think?
N?
What's the unit?
Meters.
Per second. But it cancels.
Julia? No unit. Why not? What happens to them? I heard it.
They cancel out.
Meters per second over meters per second. It's like having x over x, right? If you have units that are the same in the numerator and denominator, they both cancel. N is a unitless value. Right? It's a unitless value. Let's go to the next page so you can actually see this, okay? So you can actually see this. Here's all the values. So take a look at glass. It's 1.52. That's why I use that. I was going to use benzene. It's 1.501. But I'm like, who the hell knows what benzene is, right? Just, right? If I told you, like, okay, now light's going through benzene, you're going to be like, what's benzene again? I mean, you might know it from chemistry, but do you even know what it physically looks like? But you know what glass looks like. It shows glass. Makes sense, right? Now, other stuff on here are different materials, different liquids. These are some gases. Look at air. Why isn't it exactly 1? The air around this is not a what? What's the word I keep using? Space is a?
Vacuum.
Vacuum. Thank you. Remember, if you go back to the previous slide, you saw the n value was the speed of light in a vacuum over the speed of light in that material. Well, this is the speed of light in a vacuum. This is the greatest number possible for velocity. Nothing can ever surpass that number. So technically speaking, the denominator will never be as great as the numerator unless you're where? Where do you have to be? In a vacuum. In space or in a vacuum on Earth. A vacuum is something that has all the molecules removed. So a vacuum literally does what you think it does. It sucks all the air out of a chamber. There's an experiment, and I've talked about this earlier in here, where there's a bowling ball and a feather, and they're dropped in a vacuum. And what happens? When do they all land? When do they both land? At the same time. Because without a vacuum, there's no air resistance. Without a vacuum, there's no bending of light because there's nothing to stop it. There's no air in it. Think about it for a second. We said earlier that light slows down when it goes through fluids or when it goes through glass. It's like molasses, right? Walking through water. Well, if you're in a vacuum, is there anything to slow you down? No. So the speed of light in a vacuum is 3 times 10 to the 8. But if you think about air on Earth, there are molecules. There is some sustenance to it, I guess is the word. So this denominator will be smaller than the numerator by default. This number can never be greater than 1. This denominator can never be greater than the numerator. Okay, so V must always be less than C. Therefore, N is always greater than 1. And I could put equal to. I'll put greater than or equal to because I guess we could consider it in a vacuum. Okay, so the velocity is always less than or equal to at most C if you're in space. But on Earth it wouldn't even be equal to. It would just be less than, and it would just be a greater than symbol. And look at all your values. Obviously, they all verify this, right? Hey, which material slows down light the most? Which material slows down the light the most? Use your context clues. Come on. Almost all of you should be able to answer this. Which slows down light the most? Just look at the numbers. Ryan?
Diamond.
Why?
Because that has number.
Yeah, and if you just use your context clues, remember in air it doesn't slow down much, right? Air around us doesn't really slow light down very much at all. We said that earlier. And this is the lowest number. So by default, the highest number must slow down air the most, right? Or light the most. So circle diamond on here, please. Just jot it down. That value bends or slows down the light the most. It bends the light the most, or slows down light the most. We're going to see why this plays an important role in the next section. It bends or slows down light the most. All right, let's get to an example of this. To do this, we have to take a look at one of our equations we're going to use. This equation is called Snell's law, and all it does is it gives us a ratio. And if you think back to proportions, this comes from a proportion. You could solve this formula for Ni over Nr by moving Nr down, and it turns out to be sine theta r over sine theta I. Well, what's Ni and Nr again? I, what did it stand for earlier? What did I use the word for? Initial, or what was the other word? I said you could use either of them. Incoming, initial, or incident. I, that value is fine for all those. So I is really just the first medium. Whatever the first medium is, the end value. And R is the index of refraction for the second medium. Okay, the refracted medium. Second medium or refracted medium. So this law is going to allow us to calculate how much the light is refracted. So all we're going to have to do here is remember how to solve for theta. How do we solve for theta? How do we solve for theta? When it's in a trig function. Come on, who remembers this? We did this earlier this year already. We've done it once at least. You did it in your math course last year. How do you isolate theta when there's a trig function next to it? What do you eventually have to use? It's a certain command. It's a certain command. The inverse. Very good. We're going to have to remember to use the sine inverse in this section, okay? So if you're looking for, jot this down because it happens every year, I'm telling you. If you're going to solve for one of the thetas here, you have to use the sine inverse function. Let's go to an example. Okay, this is literally just a law. You don't have to memorize it. It's on your formula sheet. So a light wave traveling through air strikes a flat, smooth surface of fused quartz. That's just like a glass material. At an angle of 25 degrees to the normal. Determine the angle of refraction. Now, you don't really need a diagram for these because they're pretty easy, but I'll draw one anyway so you can see. So the angle is 25 degrees to the normal, so let's draw a normal. There's the normal right there. Draw a light ray. It looks like a 25-degree angle, maybe. Close. Okay, that's my diagram for this. Now, on one side, we know we have what? It looks like air. On the other side, fused quartz. If I go to my table, I can see in my table and look up the value for N for fused quartz. So we're starting in air. Air is 1.000293. For the sake of this, what do you think I'm going to use for air? I'm just going to use 1, okay? When we're using air to start, we're going to use 1. We're assuming we're coming from a vacuum. It's because we're going to have to go 5 decimals to get any significance, which is not going to change our answer. And then for fused quartz, we go to our table and see 1.458. Where am I getting this, please? For those who are really confused, how is he getting these numbers? Ryan. Please, 2 slides before. Scroll up if you're not sure where I'm looking here. In the table, 2 slides before, fused quartz and air were both listed. Since I'm going from air to fused quartz, I can see I'm going from air, which is the fastest moving medium, to something that's going to do what to my medium, or my thing? It's going to slow it down. It's going to slow it down. From the previous slide over here, when it slows it down, it bends toward the normal. So if I were to draw the normal on the other side now, continue the normal on the other side, my light ray is going to bend closer to the normal. So instead of following, I'm going to put a dashed blue line to show the trajectory that it would have continued on. It would have continued on that dashed blue line, but instead it continues on this red line. It bends toward the normal. I don't even have a number yet for an answer. See this? I didn't even use Snell's law, and I already can draw my diagram that it's going to bend toward the normal. So let's go ahead and calculate that angle theta r. That's what we're trying to figure out now. Theta r. That little angle in there that we're showing right here in the diagram. So let's use our law for Snell's law. Ni sine theta I equal to nr sine theta r. It's just plug and chug with these problems. Okay, Ni was 1 for air. Sine of the angle equals nr, which is 1.458 times the sine of theta r. Please, 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 think of this as a simple equation with x. Sine theta r is x. In your mind, put an x here. How would you get rid of 1.458? Divide through. Okay, divide by 1.458 on both sides. Cancel on the right side. That's sine theta r. What do we want? So how do I get rid of sine? What was that thing we said earlier? Take the sine inverse, not multiply. Take the sine it's a function. That's why. Take the sine inverse of whatever this number is on this side. See this number here, this sine 25, this whole thing, that goes right there. Okay, so there it goes. So take that value that's above and drop that value down below. Okay, what are you going to get for your angle when you do this? What mode does your calculator need to be on? And how do you remember degrees? Because your answer, the units are going to be degrees. It looks like the answer is going to be, I'm going to write it for the sake of time, 16.9 degrees.
So you're technically multiplying the inverse times.
Not multiplying. You're taking the sine inverse of that value. You're pressing your calculator, second sine, it takes the sine inverse of this whole thing. Sine is a function, but not until the end of this year you're going to learn about that. So it's difficult to explain why I'm saying sine inverse of. It's not multiplication, really. Okay? Let's go to the last one for today. So you guys I don't see you guys tomorrow, so you have 2 days, but you need to finish the homework from the last section and this one. This one's only 3 problems. It's really straightforward. Altogether, both homeworks might take you 30 minutes together. Okay, so it looks like a couple problems in the last one, but there's not much to them at all. A lot of it's plug and chug. It's going to get redundant after a little while. A light wave travels from air through an unknown medium. If the angle it hits the medium at with respect to the normal is 30 degrees and the angle of refraction is 12, determine the material. How am I going to determine a material from numbers? What do you suspect? What do you think? What do you think, Lauren? Yeah. Why would we use that diagram? What does it show us on the diagram?
The values of the property.
Yeah, the properties of n, the values of the n values here. So let's use that table with the n values to compare our answers. So we know that the incoming angle is 30 degrees. We know that the refracted angle was 12 degrees. I don't even need a diagram. I'm just literally pulling from here. Angle it hits to the normal is 30. That's the first part. And there's the second part I just wrote down. Now we know that it's coming from air. Well, from air means that it's coming from Ni equals 1. So the question is, what is Nr? If we can figure out Nr, as Lauren said, we can go to our table and determine what material it is. Ni sine theta I equal Nr sine theta r. And again, simply plug and chug. 1 goes in there. Sine 30 equals Nr sine 12. How do I get Nr by itself? Well, either just get the number for sine 12 and divide it, or divide the whole function over sine 12. Sines don't cancel. This is why you have to understand that these are not really multipliers anymore, right? That's why earlier I was saying sine is a function. Sine doesn't cancel on the left side. So your answer is the sine of 30 over the sine of 12. Okay, so what do? We start with Snell's law right here. We plug in our givens. We start from air at an angle of 30 degrees. We don't know what we're going into. It bends at 12. We get this value of Nr, which is 2.4.
Yeah.
If we go to our table, 2.4 is closest to diamond. Okay, that would be the material based on that N value of 2.4. Okay, so again, please, homework guys, you have two